Welcome all of you. Now we'll see single stub shunt matching. This is also called tuning. So especially when we have the transmission line, the different load impedance compared with the characteristics impedance of the line. So we need to match these both impedance whenever ZL is not equal to Z0. So we need matching network to match these two impedance. If we are not matching, then there will be a reflections of gamma at load end, so we'll get some reflection, so the power which is received may not be a full power. So we need a matching circuit like between this. So we need a matching network between this different impedance, so to match the impedance from Z0 to ZL. This is the scenario will come intentional or not intentional when we have an amplifier with a different impedance, amplifier or mixer, anywhere in the microwave circuits. Whenever there is a different impedance, so we need to match that impedance between load and characteristics impedance, or wherever in 2 points we need to match the impedance in many situations. So for that we can have the different types. So one of the type is single stub shunt matching. So in the single stub shunt matching, I will take a shunt stub. Stub is nothing but short length or finite length transmission line. This is called stub. So I will take a shunt stub, means that I will connect in the shunt way in the transmission line between load impedance and characteristics impedance. So when I want to keep the stub, I should know the two variables. One is what is the distance from the load, that is the distance from the load, and what is the length of this stub, so that I can know that exactly where I have to fix the stub and what should be the length of the stub. So and one more thing is, the stub can be two type. One is it can be shorted, is a short, or I can leave it open. So I have a two type in the shunt matching or tuning. One is open and short. So here we see one problem related to shunt stub that is shorted. So when you see the problem, you have to must like categorize whether the stub is series or shunt. So once it is shunt, I have to again further one more division whether it is a open or short. If the problem is mentioned short, so then it will be more clear, like I have to first choose the shunt, then after that I have to go to the short. So open also will be mentioned. So there is a two types in the shunt. Similarly, there is a series stub, there is a two type. So series stub, quickly how we can see that series type is between this Z0 and ZL. I will keep that one series where there is a stub. Again here I can keep it open or keep it short. So this is called series open or short matching or tuning. This is called series open or short stub matching or tuning. So this is, we'll see it later. Before that we'll go for a shunt stub and we'll see one problems quickly, and we will find out both distance and length. So in the given problem, So in the given problem, load impedance is 60 minus j 80 ohms, and this is my line impedance or characteristics impedance of the line. So I have to match this both load to characteristics impedance. So I can solve by using two methods. One is analytic method. This is purely from the expression I can solve that and find out what is the D and L, and another is using a Smith chart. So the advantage of both method we can see first. Analytic method will be more accurate and it can be easily programmed, so I can use any CAD tools and I can find out easily the D and L. I don't need any graphical tool for this, and it is taking a memory space and it is little computationally intensive. So when you come to the Smith chart, it is a simpler, it will give very faster, and I can easily interpret the answer very quickly in the Smith chart. So we see this, we solve this problem by using a Smith chart. So to get the answer quickly, and we can go with the analytic method also to find the answer. So we see the Smith chart. So this is basically the Smith chart, and you can see that this is construction of two circles. One is R circle and reactance circles. Already you know that basic construction of Smith chart. So quickly, if you see this circle from left to right, so this is, you can see that R equals to 0.1, R equals to 0.2, 0.3, 0.4. This is a R circle from 0 to, when it goes to the right, it is R equal to 10 here, and comes to here is R equal to infinity. So this point R equal to infinity, and similarly this is called R circle. So you can see that complete circles flowing like and connecting till here, connecting till this point, and similarly R equals to 0.2 circle connecting here, R equal to 0.3 is connecting here, and 0.4 is connecting here. Okay, I have a construction of R circle. So similarly, when you take that reactance circle, so reactance, it will be a positive and negative reactance always. If you take impedance, there is a real impedance. We, as for your note, we are not considering the negative resistance for our calculations. So always resistance here is positive R circle, and reactance can be plus Jx or minus Jx. It can be positive or negative. So the reactance, you can read it from the Smith chart. You can see it here, or this is x equals to 0.1, and this is 0.2. This is a 0.1 is connecting to here, and this is a 0.2, this is a 0.3, and such a way this is 0.4. This is all x value. So any impedance in the Smith chart I can write in terms of normalized value. I'll take any impedance, divide by characteristics impedance, so I'll get real part and imaginary part. So the real part is always my resistance circle that I shown earlier, and x is nothing but my reactance. So this is how can be a plus Jx or minus Jx for any given impedance. If it is a plus Jx, always it is in the top. So in the Smith chart, always the bottom is negative Jx. So once I know that where I should navigate in the Smith chart, when I know first R, then plus Jx or minus Jx, I can go top or bottom of the Smith chart. So once I know that, I have to mark the point. In this given problem, as you can see, I can just rewrite this. In the given problem, the load is 60 minus j80 ohms, and characteristics impedance is 50 ohms. So first, the step in the Smith chart is I have to normalize this impedance. This is called normalized impedance. So I take the given impedance, I will divide by characteristics impedance. So I will get roughly 1.2 minus 1.6J. So this is my normalized impedance. So the very first step in the Smith chart, I have to mark the point, the normalized impedance in the Smith chart. So when you see the Smith chart, so I have to mark where is my 1.2 minus 1.6J. So here I'll just rub it off all the points which is not necessary now. So first I have to mark this normalized impedance of ZLN of N. So when I go here, so R is 1.2. So R equal to 1 circle is here in this point, and R 1.2 is here. This is R equal to 1.2 circle, and X is minus 1.6. So in the R equal to 1.2 circle, I have to go all the way till 1.6J. This is plus Jx. I told earlier this is minus Jx. Since it's the minus, I should come bottom of the Smith chart. So I have to go to in the bottom part till it is 1.6. This is 1.2. This is 1.2 reactance. This is 1.6 reactance, 1.4 and 1.6. So in this R equal to 1.2 circle, resistance circle, I have to go to the reactance of minus 1.6. Exactly the point will come here. So this is my normalized load impedance. So once I know the normalized load impedance, so what I can do is, so this is a normalized, this is 1.6 and this is 1.2. This is normalized load impedance. Okay, so once I know the normalized load impedance, I have to convert this to the admittance circle. The reason why we have to convert into admittance circle, because this is basically the shunt. So whenever in the shunt component, we always tell in terms of admittance instead of impedance. So it will be easier convention for seeing the circuit in the shunt. It is easier to like denote in terms of admittance. So if I quick change this circuit in terms of admittance, this becomes YL, and this becomes Y0, and still YL divided by Y0 is YL normalized value. So this is, we found only ZL normalized value. To find out YL normalized value, I can convert this ZL to YL by taking inverse, and Z0 also I can take it inverse, then find out YL minus Y0, and I can find out YL normalized. Or else I have a shortcut method in the Smith chart. If I know the ZL of N, if I do that lambda by 4 wavelength towards the generator, so I can, that is 180 degree rotations in the Smith chart, I can get the admittance scale. So instead of converting from ZL to YL by numerical, in the Smith chart I can mark the admittance scale directly. If this is a ZL, I will rotate these points to 180 degree towards the generator, and I will mark there with the same radius. So that point is nothing but YL enough. So to get that the value, what I will do is, I will put one straight line from load to right side to the 180 degree. So here if I have to make sure that you are doing exactly, with the more accurately you are plotting this line. So since all the value is accuracy is important, so I have to be a little more cautious to select that the point exactly. If you see that 180 degree of these rotations, so in the upper scale, so where it is exactly, I want to know the same radius in the 180 degree. So for that I need to put the circle to connect this. Okay, you take a compass and make it, this is your origin, and you know the radius of the from the origin to the load impedance, and take a compass and put on circle. So here if I do the same, once you draw the circle correctly, you can see that the origin and this is your locus of the circle, and you plot the circle, and now it's 180 degree rotations to the generator. Always you know that the Smith chart, so always the clockwise direction is is towards the generator, wave towards the generators. This is this is a wavelength towards the load. So this is a wavelength towards the generator, this is a wavelength towards the load. So 180 degree, if I rotate towards the generator, I'll get the YL point. So the YL point I can read now. This is a normalized, this is normalized admittance. You can read it from the like reactance scale. That is normalized admittance is nothing but, here reactance is 0.4, that is J plus, and what is the resistance? So resistance is 0.3. So I can write YLN of N is nothing but 0.3 resistance, and J.4 is my reactance. So once I know that normalized admittance, that is exactly this point. So now in the given problem, so I have to find out the matching. So from this admittance, always you know that whatever point in the Smith chart it is impedance is normalized, and always the matching is nothing but I'll try to bring this point to the center. Always the center point in the Smith chart is the matched, properly matched. You can verify that for any given Z0, and if you take ZL by Z0, if ZL equal to Z0, you will get always normalized impedance is 1, that is R, and J becomes 0. So reactance becomes 0, and always resistance becomes 1. So always R circle will be 1, and reactance is 0. This is X equal to 0. So always the center point is the proper matched condition. So whenever this moving away from the center point is going for a unmatched. Now the YLN of N, that is load admittance, normalized is away from the load. I have to bring it to the center. So the one of the technique is I have to bring this YLN of N to that the resistance, now it is 0.3. If I bring this 0.3 to the 1 resistance, so now the condition is partially met. The meaning that if the load, whatever my given impedance, if I make this R resistance to 1, so I completed that resistive part of the load impedance is properly matched. So the next step is from this plus Jx, if I add minus Jx to my transformed admittance, if I add minus Jx, I can bring it, this both terms will be cancelled out. So I'll get ZL equal to only R term, this reactance I can cancel out. if I make it to 1, so now I made it my admittance to the properly matched admittance, that is 1. Okay, so here the next very step is what I have to do is wherever this admittance, I have to bring it to r equals to 1. This is r equals now in 0.3. I have to bring it to r equals to 1. So to do that, what I have to do is I have to know where is r equal to 1 circle. I know that r equal to 1 circle is here. This is r equals to 1 circle. So in this r equal to 1 circle, where this VSWR, this is called VSWR circle. You know that when I have a constant circle on the any impedance, load impedance, so that is give me the VSWR circle. This is called VSWR circle. So the radius of the circle remains constant, so that S VSWR also can be written as S. This is 1 plus gamma divided by 1 minus gamma. If the VSWR is constant, that is meaning that it has a definite gamma value. This radius is nothing but gamma. So if the gamma equal to 0 means yes, I will get 1, and you can see that in the scale, the middle value of the scale always in the VSWR chart, this is SWR, you can see that always the middle value, that is the top scale, always will be the 1. Okay, so whenever gamma equal to 0, it's a center of the circle, it's nothing but VSWR equals to 1. Whenever you have start getting the radius, it's nothing but you are having some value for a gamma. It's like maybe 0.2, 0.3 value. So you have S is no more 1, it is moving away from 1. So it can be 1 moving from 1 to 2, and when it reaches out, it becomes the infinity. That time the gamma becomes, this is my reflection coefficients 1, gamma, this is my SWR. So when I reaches the outer scale of the Smith chart, so gamma becomes 1 and SWR becomes infinity. Whenever the center of the Smith chart, SWR equals to 0, sorry, SWR equals to 1 and gamma equals to 0. Okay, this is the basic of the Smith chart. So in the SWR scale, now I take the normalized admittance, I moved into the R scale, moved into in the R resistance circle till R equals to, when I have to move till I reaches R equals to 1 circle. This is R equals to 1 circle. This is R equal to 1. So these point, I have done half of the work is done. I moved my load admittance to the matched admittance condition, that is 1. So here I move this point to here. So to make this move, this is the initial wavelength at the load, that is outer scale, that the wavelength towards the generator. We can see that at load admittance, normalized load admittance, this is my wavelength at the load. When I want to move to this point, so how much distance I am moving? That is nothing but my d1. So from this point to this point, so I have to move from the load to the r equals to 1 circle. To move that to the circle, how much wavelength of the transmission line I should add, so that I will get r equals to 1. Okay, the r equals to 1 also I can write g equals to 1. So both are same. So if I move that distance d1 till it reaches to r equals to 1, so for that I should know that what is the wavelength at r equals to 1. So I'll put one more like straight line from the origin, so connecting to the r equals to or g equals to 1 circle, so matches with the VSWR of the transmission line. So intersection of VSWR, so intersection of the VSWR circle and with the r equals to 1 resistance circle, that is my r equal to g equals to 1. So that point from the origin I connect to the outer scale of the wavelength. This wavelength reads now 0.2 0.0176, sorry, this is approximately 0. So this point is the wavelength approximately read is here is in the r equal to or g equal to 1 point connecting with the VSWR is approximately 0.176 lambda. So here wavelength is 0.065, here is wavelength is 0.176. So now I have to move from load, it means to say here from the load point normalized, I have to provide the stub length of T1 so that now I reduce my admittance to 1 plus. So here if I from the load, if I move distance d1, so I will get the wavelength that is approximately the difference between these two, d1 I will get approximately 0.110 lambda. Okay, so this is my distance. So from the load admittance, if I move the distance of 0.110 lambda, so I will reach this r equal to g equals to 1 circle. So now my half of the match is done. So once I know the distance, then I can connect the stub of the length L1, so I can cancel out the imaginary part of the load admittance. So now if you take that, if I move from here to here, my conductance or R becomes 1, meaning to say this y1 now becomes 1, that is y1 in the form of G plus IB. This is a conductance and this is a susceptance, that is 1 by x, B is nothing but 1 by x and G is nothing but 1 by R. So here in this point is nothing but conductance is 1 or equal, because R equals to 1 by 1 is again 1, and this point is my susceptance. The value of susceptance here is I can read out here is, you can see that what is the resistance part here is also, we can see that this is also be a capacitive susceptance and also becomes the inductive reactance. So we can also read that directly from the reactance scale. This is 0.9, 1.0, this is 1.2, 1.4, and this is between, this point is between 1.4 and 1.6. So closely you can scale down, this is the difference between these two is 0.2. So each scale division is 1, so totally 2 division is there, so each division is 0.1. So this is 1.5, the middle one, and this point is not exactly at 1.5, it is little less than 1.5. So if you approximate it, so we'll get y1 is 1 plus 1.47j. okay, so this is my admittance on this point. So I have to add the stub length of L1 of minus 1.4j to cancel out this susceptance part of admittance. This is the basic idea of single stub matching. So in this process I will also come to know there is a point from y1 of n to y1 on r equal to 1 circle, and also that I can reach this r equal to 1 circle in another point, that is here the bottom of the Smith chart. Here also the VSWR circle is going to meet G equal to 1 circle or R equal to 1 circle in this point. So if I read out this value again, I will get closely the same conductance, and instead of plus 1.4 I will get minus 1.47j. You may wonder like it is not exactly VSWR and width. You can see it is like giving 1.5 because I have drawn in the circle in the approximate value, but when you do that actually the compass will get exactly plus 1.4j. This is bottom one is minus 1.4j. So this is I call as y2, this is y1. So what is the idea here is I'll get the distance not 1, I can even have a another distance. I have a two solutions for a same problem. So I can go and choose d1, or I can go and choose from yl of n all the ways to till this point. Okay, and I can put again another straight line from the origin to this point r equals to VSWR circle, which is connecting with the r equals to 1 circle. Okay, so this is my y2. So from the yl of n I can move all the ways to that g equal to 1 circle, so that real part becomes the 1. So this distance called d2. Okay, so this initial wavelength of load I know 0.065. What is the wavelength of second distance from the outer scale? I can mark this point is approximately 0.325 lambda. So now difference between these two, 0.325 lambda minus the what is the load admittance, 0.065 lambda. So now this becomes the distance 2. The distance 2 I will get as 0.260 lambda. So now the stub from yl of n I can choose d1, or I can choose the d2 distance of 0.260 lambda. So I have a two solution for one problem. So in practical situation, which one I will choose it? Always my stub I'll choose closely to the load. The reason is there are dissipations, that reflection, whatever if even there is a mismatch here, some of the power is going to reflect here. So if I keep the stub as close as possible, I can reduce that power dissipation. So always in a practical purpose, always the distance of the stub from the load I will always choose minimum as possible. That is for a practical purpose. Now for a completeness of the problem, we will find out two solutions for this problem. Once I know the distance, my half of the job is done. Now other thing is I want to cancel out the reactance part of these two admittance y1 and y2. Now from ZLN we'll put 180 degree. I got yl of n, that is a normalized admittance. From the VSWR circle I move to all the ways to r equals to 1 or g equals to 1 circle. I got the 2 points y1 and y2. From moving from here to here, what is the wavelength? It's nothing but first distance. From moving this yl off to another point, that is d2. Okay, so I'll get two distance. For practical purpose, I will choose that always d1 is lesser enough. So once I know the real part of the admittance, now that time I have to cancel out the reactance part. So for first y1, I have to choose that length of the stub is minus 1.4 j, and a second for a second distance I have to choose that plus 1.4 j of the susceptance to cancel out this susceptance value in the new y1 and y2 value. So to do that, first I will mark it out where is L1 in the Smith chart. So if I see in the Smith chart, I will always taking now in the Z chart only. Always bit cautious, like when you are once you move to the admittance scale, now everything, all the values you are doing with the Z chart only. Even the reactance, whatever reading is plus 1.4 j, that is in the Z chart. Always in the Z chart, this is a positive and this is your negative. And similarly, here for a reactance of minus 1.4 j will come in the bottom in the Z chart, in the normal Smith chart. This is minus 1.47 j. Sorry, this is minus 1.47 j. So here I have to mark this point closely. This 1.5, between 1.4 and 1.5. This is my 1.4 j minus 1.4 j. This is my L1. I'll just put one straight line to make sure that what is the wavelength at that reactance. This is my L1, that is minus j 1.47 j. Okay, similarly I mark L2, that is plus 1.47 j. So this is 1.4, this is 1.5. Between this value I will get closely here, that is minus, that is my plus 1.47 J. So here I will put another straight line to the outer scale so I can find out what is the wavelength. So now this is called L2. So now the tricky part is, now this reactance in the Z chart. Now from the load I found the distance. Now I should add the length of the stub. So when I add the length of the stub, I know what is the susceptance. But the Z chart, this is a positive, this is my negative reactance, that is imaginary part of the impedance. But in the admittance chart, this is a reverse. So it is a susceptance. Reactance is called susceptance. What I have to do is, from the L1, this is a impedance in the Z chart, I have to again rotate 180 degree. So this is a little, I have to be, remember this step, this is a little bit, I have to like keep it in mind. So from the L1 of whatever wavelength I got here, this is my point. So I have to draw one more, I'll use that another straight line here. From here I have to through the origin, I have to put another 180 degree straight line connecting to the other end of the Smith chart. Now this is actually in the Z chart, this is my reactance. If I rotate to 180 degree, it becomes the susceptance. So now in this length L1, in the susceptance domain, that is nothing but shunt admittance domain, I mark this the wavelength. So since it is a shunt admittance, this is a shunt, again the stub is also shorted. The always shorted stub will have that 0 impedance and infinity admittance. In the Smith chart, always this R equal to 0, X equal to 0 and Z equal to 0. Impedance is 0, meaning that admittance equals to infinity. Now the right side of the Smith chart, so if you take that right end of the Smith chart, this is R infinity, X is infinity and admittance is infinity, impedance is infinity, but admittance is 0. So here I know this in admittance scale what is a susceptance. From the, because since the stub is shorted, I'll have that infinity admittance, that is y equal to infinity or z equal to 0. From here I have to move my wavelength toward the generator. From here I have to move all the way till this admittance. So if you see, read this reading, this is nothing but the value you closely you get around, you can read from the circle, it's 0 and it's a 0.095. so the distance is closely, you'll get this is 0.09, this is a 0.1, so you'll get closely the distance from this y equal to infinity to here is my length of the first step, 0.095 lambda. So similarly for L2 is a here positive, I have to convert into y domain. I will take another straight line all the way from the origin connecting to the outer scale of the Smith chart, that is a wavelength. So once I connected to the outer scale, from the y equal to infinity, because it's a short stub, so y equal to infinity or z equal to 0, from the generator, from the beginning here, this is y equal to infinity, from the stub end point, because stub is always shorted in this point. This is my stub, admittance always infinity, that is impedance is 0. From the shorted point of the stub, I will move all the way till I get this. I'll just move all the way from here. Is that equal to 0 or y equal to infinity? I will move all the way till L2, the susceptance value of L2. So if I see the total rotation, that is my L2 of the second stub length. So if you total of rotation is, you know, that 0.25 lambda, and remaining rotations you can calculate. So difference you can see that is around between 0.4 to 0.41. So you will get the length of second length of the stub 0.25 plus this. So you'll get closely length of the second stub is 0.405 lambda. So the solution, the two solution for a given shunt stub short matching or tuning is, we get two solutions for Z0 50 ohms to the load 60 plus 80J. I will get a stub, shunt short stub. The distance is d1.110 lambda. The length of the stub is 0.095 lambda. In the second solutions, we'll get distance 2 is 0.260 lambda. Length of the stub is 0.405 lambda. Suppose if I choose the frequency, operating frequency is 2 gigahertz, then ZL, it is a negative reactance, so I can use the capacitor for that. It can be written as RL plus, this is minus actually in the problem, so JXL. So XL is nothing but, right, 1 by, I can take, this is XC for a capacitance, 1 by J omega C. So if I put omega equal to 2 pi f, and I will get C is roughly 0.995 picofarad. So the complete design of the stub matching will be, I have a resistance of for example the given problem is 60, and the reactance of capacitance 0.995 picofarad, and the length of the stub of first 0.095 lambda, and distance of the first stub is 0.110 lambda. So this is complete the solution. Similarly, I can write this D2 with and L2. I will get a two solution for one given problem. So I can find out what is the distance from the load, and also I can find what is the length of the stub. Thank you for listening.